This is Power of the Test, Part 1. So, the power of a test is best described as the probability that a test will correctly reject the null hypothesis. The null hypothesis has always been our default position. You can imagine thinking in terms of alpha and beta. Alpha is the chance of type 1 error. How likely is it that you will reject the null hypothesis when you should have failed to reject it? Beta is the opposite. How likely is it that you will fail to reject the null hypothesis when you should have corrected it? So our power ends up being 1 minus beta. Now, as we go through these examples to help illustrate these ideas, I'm going to only stick with one-tailed tests. In other words, these are going to be only tests of improvement. Makes it a little easier. The main purpose of power of the test is it helps for a repeated test. Let's suppose that you run your experiment, you run an analysis, and you discover statistical significance. Power will tell you how likely is it that when other people run the exact same experiment you did, they will also find statistical significance. So let's begin. Step 1, find the critical sample mean. The critical sample mean is the maximum or minimum your sample mean must be, but still achieve statistical significance at any particular alpha. So we have that subscript alpha there. I say maximum or minimum because it depends on if it's a plus or a minus. It depends if what's interesting is really, really low, like faster times, or what's interesting is really, really big, like more sales. This is our null hypothesis, our population mean. This is our one-tailed z-scores. This is our population standard deviation, and here's our, as always, our sample size. So let's imagine our first scenario, stronger truck. Suppose that the average truck, commercial truck or personal truck, can haul an average of 8 tons with a standard deviation of 0.9 tons. And you're like, I'm going to make a better truck. I think I can make one that is an improvement over this 8 tons hauling. So you make your truck. You make maybe 9 prototypes and you test them. What's the smallest amount they can haul and still achieve statistical significance and still be able to say this is an improvement over before? It probably isn't random. And we'll put that at the 5% level. If you want, you can go ahead and pause the video and try to calculate that yourself. So you should have gotten about 8.5 tons. Here's our average of 8. Here's our 1.645 is the critical value of Z at 5% or 95% confidence. Here's our standard deviation. We have 9 trucks, 8.4935. If you do this with a statistical significance of 99% or an alpha of 0.01, what do you think will happen to the critical sample mean? That's right, it should increase, and indeed it does. Right, the only thing that's changed is this z-value, and of course the z-value has gotten larger, so we've gotten farther away from our population mean. You need about 8.7 tons to haul. Go all the way up to 99.9% significance, or 0.001 alpha, almost a 8.9. In other words, as alpha shrinks, the critical sample mean gets farther away from the population mean. Right? And that makes sense because this area is now smaller. Let's go in a different direction. Let's imagine faster processing. Let's imagine that you work at a company, you get these orders in, and they're trying to turn these orders around as quickly as possible, ship things out as quickly as possible. Let's suppose it takes an average of 4 hours to process an order with a standard deviation of 1.2 hours. And you come up with this different way of processing orders where you think this is an improvement. And you maybe test this on, say, 16 orders. What is the longest amount of time that it can take to process an order with your new system, but still achieve statistical significance, still be able to say at the 5% level, an alpha of 0.05, that this is an improvement? So you can go ahead and you can do the math and pause this video as you calculate. you should have gotten about 3.5 hours. Note now we're subtracting because lower numbers are interesting. Right? Lower numbers indicated an improvement before higher numbers indicated the improvement. You haul more things. Now we're processing the order faster. 1.645, as always, is a critical sample, one-tailed test, a 5% level. Again, here's our standard deviation. Again, here's our sample size. And if you decrease alpha to 0.01, you should get, that's right, a lower number for your critical sample mean, because now you're subtracting off more. Now, in order to claim statistical, you have a higher standard, 99% confidence. Now, in order to claim statistical significance, you're going to have to do even better. 3.3 hours rather than 3.5. Or at a 99.9%, just over 3 hours rather than 3.5. Huge improvement in order to claim, yes, this is actually a difference. This is a better system. And again, you decrease the alpha, the critical sample mean gets farther away. So it works in both directions. Thanks for watching, and join me in part 2. We go over the next step in determining the power of a test.